All right, hello, and we're live. My apologies to everybody who saw something pop up and then saw it go away. I clicked start streaming before I had my mic plugged in, so that would have been a very quiet, very confusing office hours. I don't think it would have taken that long, though. You all would have been like, we can't hear you. We see your words, but we can't hear you. So anyways, but we avoided that situation all together. All right, welcome to office hours. I am down to take any questions. I think I have one email asking about questions, so I can answer those. Answer those in the absence of any live questions. But of course, if you are here live with me and you have questions, I'll totally answer yours first. But I'm going to start pulling up my start logging into my textbook so I can get answers to the email question. But I am ready for questions. Let's see. Alrighty. Oh, Rachel. Okay, let's see. Experiment 2, 22% error for chlorine. Checked and checked again. What I could have done wrong. Okay, so a couple things. Something to keep in mind. Rachel, this is Yeah, totally. I can totally walk through Rachel and Logan. This kind of will, I think, address both of your questions. I can totally walk through the calculations. You can see, okay, this is how we would calculate the mass percents. But something to keep in mind, and this is really important, is the data sets that we're giving you this semester are we're calling dry lab data. The name is chemists, when we talk about getting results from lab, we call them wet, because usually you're doing solutions. So when we say wet lab, that's a lab that you've actually done. A dry lab is one where there are no actual chemicals involved. And so all of the data is dry lab data, but that doesn't mean that every time that we're giving you a pristine set of data that your numbers are quote unquote accurate or correct. We may be giving you data that has inherent flaws, much like the flaws in data that you would collect if you were in lab yourself. So just because a calculated value doesn't seem quote unquote right, doesn't mean that your calculation is wrong, because it's a very common thing to experience when you're in a lab class, where you do the calculation for the data that you collected and it's not what it quote unquote should be. Also, keep in mind, one of the points of this lab is learning how to calculate a percent error and use that as an evaluation tool. So I would not be surprised if your calculations do end up being correct. for the data that you were given. Now, that being said, let me get a set of data so that I can kind of run through the calculations and you can compare what you did, because there could have been a mistake on your end, but there may not have been. We will soon find out. All right, let's see. All right. There we go. Okay. All right. Yeah. Also, totally helps to check out the situation with your digital lab partners as well. Can add a boost of confidence. Okay. Let's see. I'm looking at. I'm going to create a set of data for myself. Oh, you know what? Let me just make sure that these are somewhat ballpark to the data that you've been given, because I also don't want to just like pick some sort of pristine thing for myself. And all right, so let's go. Oops. Oh wait, hang on. Right, there we go. Let's try that on for size. And then there. Plus. All right. Okay. So here is the data set that I'm going to be using. I am going to be, so this is an experiment. Oops, no, sir. Let's go like this. So this is for experiment 2. And my data set will look like this. So, anhydrous calcium chloride. For my mass of anhydrous calcium chloride, I'll have a mass of 0.1005 grams. My calcium ISE reading is 381.0. And remember, this is milligrams per liter. Oops, I need a bigger eraser. There we go. And my chloride ISE is 595.4 milligrams per liter. Okay, and the second thing that I'm going to do is pull up my hang on. There we go. Let's go to pages. Okay. Whoops. That's what I want. Okay. Let's take a look. Okay. That's what I want to see. Okay. So this is our data that we're given, and we are being asked to calculate a few things. First, the percent calcium, and again, these are both by mass. Percent calcium by mass, percent chlorine by mass. We're asked to find the empirical formula. Actually, lots of things. But let's go ahead and run down percent calcium and chloride. All right, so actually, yeah, that's right. I need to open a new slide. All right. So let's start with percent calcium by mass. All right, percent by mass for calcium is equal to the mass of calcium, right? The grams of just calcium divided by the grams of calcium chloride times 100%. All right. Now, our denominator here, grams of calcium chloride, we have this right up here, right? That's the massive anhydrous calcium chloride that we're given. The real question is, how do we get this mass of just calcium? And it's going to come from your ISE reading, but there's a problem. And that problem is the denominator. The ISE reading gives you a ratio between, it's a concentration. It gives you the mass of that ion, which in this case is calcium, tells us that there's 381.0 milligrams of calcium in 1 liter. All right. So we need to know what volume of a solution was used to make this measurement. And that is where the 100 milliliter volumetric flask comes in, right? And I talked about this in the lab lecture that I did a couple days ago. This solution was made in a 100 milliliter Erlenmeyer flask. Whoops. The reason why I said whoops there is because not Erlenmeyer flask, volumetric flask. And volumetric flasks have 2 decimal places. Now, we still can't quite cancel because liters and milliliters are not the same volume unit. But if we apply the unit conversion for milliliters, put milliliters in the denominator, liters in the numerator, 1 milliliter is 10 to the negative third liters. So these cancel. And then liters cancel liters, and we're left with just milligrams of calcium. Now we're close, but we need grams of calcium in our numerator. So we are going to need one more unit conversion in here to convert from milligrams to grams. All right. 1 milligram is 10 to the negative third grams. So milligrams here cancels milligrams here. And now we can calculate our mass of calcium for our numerator. So we have 381 times 100 times 10 to the third times 10 to the negative third, times 10 to the negative third again. So we come out with a mass for calcium of 0.0381 grams of calcium. All right. So our percent mass of calcium is 0.03810. Hang on. Okay, sorry. I'll be back in 1 second. My kids are fighting in the next room, and I have to intervene. I apologize. I will be back in 1 sec. You dudes, your entire fight is getting broadcast to YouTube. So I need you guys to please be quiet. Okay, guys? Could you please work out your thing peacefully? Okay, let's see. 1, 2. Okay, sorry, just checking the mic to make sure we're back. I apologize for that break. You may have noticed in the interim that we actually landed with the incorrect number of sig figs, right? We have we have 1, 2, 3, 4 there, and we have 1, 2, 3, 4, 5. We got to roll with the fewest, and I wrote down a number that only had 3. So this is our mass of calcium, which goes in our numerator, over our total mass, 0.1005 grams of calcium chloride times 100. Okay, so we can crunch now our numbers. 0.0381 divided by 0.1005 times 100. Okay, so we're getting for our percent of calcium from our data is equal to 37.91%. All right, so that's our mass of calcium. Let's calculate our percent mass of chlorine. Now it's going to be the same deal. Our percent by mass of chloride ions will equal our grams of chloride over our grams of calcium chloride. Again, we know our mass of anhydrous calcium chloride. We need to use our ISE to determine the mass of chlorine. So let's take a look. Oh, and Rachel, also everyone else listening, for the record, the numbers that I'm getting are from a data set that's different than the numbers that you're getting. So all I did was I looked at the student assignment list for the data set, and I picked numbers that were like ballpark in the middle of all the numbers that I saw for those. So if my numbers are different than yours, it's because my data is different than yours. The two ISEs and then the mass of anhydrous calcium chloride. So as long as you do the same steps, you can be 100% confident that your number is correct for your data, all right? And that's all that matters. Even if your number has a huge error margin, if your calculations are correct for your data, you'll be getting full credit. So that's the important thing to focus on here. Now, again, our ISE reading for chloride tells us that there are 595.4 milligrams of chloride in 1 liter. All right. We again multiply by our volume, which is the volume of the volumetric flask. All right. But again, we run into that thing where milliliters and liters do not cancel each other. So we need to convert from milliliters to liters. All right. 1 milliliter is 10 to the negative third liters. So liters cancel and milliliters cancel. Next, we need to cancel milligrams because we don't want milligrams of chloride, we want grams. And 1 milligram is 10 to the negative third grams. So now milligrams cancel milligrams, we're left with grams, which is good. And we're ready to crunch some numbers. So we go 595.4 times 100 times 10 to the negative third times 10 to the negative third. So this comes out to be 0.05954. This is grams of chloride. So now we're ready to actually calculate our percent mass. 0.05954 grams of chloride over 0.1005 grams times 100. All right, so based on my data, my percent, mass of chloride, again, from my data, is equal to 59.24%. All right, now these are numbers based on my data. Make sure that you remembered to, do all the proper unit conversions along the way. But assuming that you did, you can be confident in your numbers, even though they will be different than mine. Now, let's go ahead and take a look. So this is how you do the data or the calculation for the percent masses based on data. We know that percent error, I'm going to need to clear a little room here, that percent error, which we need to calculate for each, is the absolute value of the experimental value of whatever it is we're talking about minus the correct value over the correct value times 100, because that's what makes it a percentage. Leanna, 2.522% error could be totally spot on. It may not necessarily be from rounding. I doubt it would be from different periodic table masses. It's probably because the data in this set was put there to be purposefully incorrect to give you some meaningful data. Because if everybody did the percent error calculations and everybody got a 0% error, that wouldn't actually tell you anything. So I'm pretty certain that flawed data was assigned on purpose. The reason why I say pretty certain is myself and Dr. Cheng and Dr. Gillies are all taking turns writing the labs for this class. And so this was one that I did not create this set of data personally myself. And so, but if I was, I wouldn't do data where everybody gets a 0% error. I would give you data with some error in it so that the error calculation would be meaningful, if that makes sense. All right. So this is the calculation for percent error, and when we calculate the percent error for our data for calcium, percent chloride that we got from our data, this is right here. The experimental value are the ones that we just calculated. What we need to know to get the percent error is what are the correct mass percents of calcium and chloride. And to get those, we need to calculate these from the molecular formula for calcium chloride. All right. So to get these percent errors, we need to look up some atomic masses. And I need to bust out a periodic table. All right, so calcium has an atomic mass of 40.08 AMU. Chlorine has an atomic mass of 35.45, but here we're dealing with two of them. So that'll be 70.90 AMU is the atomic mass of two chlorines. Okay, solid, Rachel. Totally solid. And yeah, and if you double check and it comes out the same as what you already had, you can be confident that you nailed it. So our atomic mass for calcium chloride, sorry, not atomic, molecular mass. Let's see, it'll be 70.90 plus 40.08 is 110.98 AMU. Now we can calculate our correct values for the percent mass of calcium, which will be 40.08 over 110.98 times 100. Percent mass for chlorine will be 70.90 over 110.98. Oops, not equals. Times 100. So let's crunch these numbers. 40.08 divided by 110.98 times 100 is 36.11%. For chlorine, 70.90 divided by 110.98 is 63.89%. So these right here are our correct values that we're going to use for the percent error calculation. Let's see. Amanda. That that periodic table that you're using is totally correct. It's actually slightly more precise than my periodic table. You don't need to worry about differences in periodic tables resulting in you getting the answer wrong. Totally don't sweat that situation. The reason why they're different numbers is because the instruments that we use to measure atomic masses are getting better as time progresses. We're getting better and better at building them, and so we're getting more and more accurate measurements. And so periodic tables get outdated, just like any scientific book. It's only as good as our ability to measure and observe at the time. And so often you'll run into periodic tables where the decimal places stop at 2 and then go to 3 and up to 4. And it'll also vary. There are some that have 4 decimal places for some elements and then 2 for others, because some elements are just harder to measure. So you don't stress about using quote unquote the wrong periodic table. Logan, here's what I would say. It totally depends on the sig figs of the atomic masses that you're using. But I will say this: there's no periodic table that'll give you atomic masses with less than 2 decimal places. So these should all have at least 4 sig figs. So your 36.12, spot on. Your 63.9 though, I would say you need a second decimal place there, if you want it to be acceptable, if that makes sense. Now that we have our correct values, we're ready to calculate some percent error. All right, so I just needed to remind myself of what my experimental value is. Amanda, you are welcome. All right, so let's calculate the percent error. For calcium. Percent error for calcium. So we have the absolute value of our correct value, which is for calcium is 36.11 minus my experimental 37.91 over the correct 36.11 times 100. Now we have to be careful here because we're switching in between operations. We're going to do subtraction, then division. They have different rules for sig figs. So first, 36.11 not divided by 36.11 minus 37.91. When I punch that into my calculator tells me that it's the answer is 1.8, but I have to look at my sig figs. Both of these numbers have their last significant digit in the second decimal place, so my answer must have its last significant digit in the second decimal place as well. All right. So we have that over 36.11 times 100. All right, absolute value just turns any negative into a positive. So this is just 1.8 over 36.11 times 100. Now 1.80 divided by 36.11 is, and then times 100 is 4.98476.876. I have 3 significant figures in my numerator. I have 4 significant figures in my denominator. I'm allowed to keep 3 because I got to roll with fewer. So 1, 2, 3. This 4 rounds down. So my percent error for my data with calcium, error. There's an O there, not an A. For calcium is 4.98%. That is the correct value with the correct sig figs. All right. Running through with chlorine. So our percent error for chlorine, we've got the absolute value of our correct value, which is 63.89%, minus my calculated, which is 59.24, over the correct value, 63.89. I don't need these percentages. Let's see, 59.24 times 100. All right. 63.89 minus 59.24 divided by 63.89 times 100. Oh, wait. Let me take this one step at a time here. First, 63.89 minus 59.24. It's really easy, as you saw me just doing, or heard me just doing, I guess. I'm just punching all the numbers, but you got to remember, different rules for sig figs means that we got to keep track of them as we go. So the difference in the numerator, when I punch it into my calculator, tells me that the answer is 4.65. Looking at sig figs, both of these numbers have their last significant digit in the second decimal place. My answer does as well, so no rounding or additional zeros are needed here. This is over 63.89 times 100. So divided by 63.89 times 100. This comes out to be 7.27813.429. We have 3 sig figs in our numerator. We have 4 in our denominator. So we have to limit our answer to 3. 8 rounds up. So our final answer for my data for the percent error of chlorine, make that CL a little bigger, is 7.28%. That is the correct value with the correct number of sig figs. Again, if you watch your sig figs, as you can see, the way that mine worked out, I only ended up having 3 at the end. Amanda, here's the cool thing. That is a great question. So Amanda asked, is it experimental minus correct or correct minus experimental? It does not matter because you take the absolute value at the end. Because you take the absolute value, that'll pop any negative into a positive. So the absolute value of experimental minus correct equals the absolute value of correct minus experimental. So it doesn't matter. I may have actually flipped them around from what I wrote out earlier, which may be the source of your confusion. But the reason why I was sloppy is because in this instance, the value will come out the same. All right. Okay. I'm so sorry. So, Hannah, I was just scrolling back up through the things, and I totally missed your question earlier. My apologies, and thank you for being patient. It is totally possible to get percentages for calcium and chlorine that are greater than 100. For the experimental data. That is totally possible. If you're doing it for the correct values, they absolutely shouldn't be. But for your experimental data, it is possible to have your percent calcium plus your percent chloride being above 100%. Actually, I don't even know if mine is. Let's take a look. I think it's down here. Nope. There we go. It may or may not be. Let's see. So for me, 37.91 plus 59.24. Okay, so check this out. For my data. Oops, no. I'm going to write it right here. For my data, 37.91 plus 59.24 adds up to be 97.15%, less than 100, which we know it's not. If it's only these two things, it's impossible to be less than 100%. But that's just more evidence that there's error in our data, that our data somehow is flawed. Whether it was human error, whether it was instrumentation, there's a bunch of different places error can come from. And it's not horrible. It's not like my percentage is like 72. That would be like, okay, something's massively wrong. With yours, I'm guessing it's a little bit over 100, but I'm guessing it's not 130. It might be 102 or, whatever. But that is totally normal when you're dealing with real data. And again, part of this online eLab situation is we're trying to give you as real an experience as we can. And with real lab data, it's never perfect. So that's reflected in our percent errors. It's reflected in things like this. My 2% mass percents of calcium and chloride are less than 100. Yours are greater, but it's all okay. All right. Because what you're being graded on is, did you take the data and do the calculations with it that you should have? You're not going to be judged on flawed data that you were given, because the flaw is part of the teaching experience. All right. Okay. I am, again, totally down to take any fresh questions from the live feed. I do have a couple questions from the textbook homework that I'm currently loading. Man, a great question. Okay, Rachel, let's see. I was wondering, when will we get... Oh, okay. Awesome. Rachel, great question. Right, okay, so... Okay, Rachel. Great questions. Two things. So first off, I actually just... I was working on it, finished it up today. I finished it up right before... office hours started, and then I what's the thing I'm looking for? Sorry. I uploaded it, but I didn't quite finish writing the announcement that the review packet was done. So you can, so it's actually up live on the Canvas page, probably in a place where no one can find it. I swear I'm not trying to hide it. And in the post that's coming later, I'll add some links. Here, speaking of links, let me drop one right here. So I added it under pages in Canvas, and I'm gonna link to this in my announcement. But on Canvas, you know how you have like that like side kind of panel thing? It'll say like home, announcements, grades, like all this good stuff. That's grads, grades. Dot. If you go down to pages on that kind of navigation sidebar and click it, it takes you to this place that looks like the home page. It'll say like welcome, but up in the top there's a little button that says view all pages. And when you click that, it takes you can view all the pages. Actually, there. I just changed it so that the front page for pages is now exam review packets. How about that? That's a lot simpler. All right, so when you click on pages, it instantly takes you to the exam review packets, which has 2 links right now. One to the prereq exam. Oh, you know what? I just realized I changed it for one lecture. You might be in the other lecture. Oh, wait, no, that's the front page. I did it for that one. Let me find, where's my other lecture? Here we go. Let's go to pages. Let's view all pages. I want to make this one the front page. There we go. Oh, wait, you know what? That's lame. I don't want that as the front page. Because, hang on. I want the welcome page as the front page. Okay, so I take that back. Sorry. Again, I'll be posting an announcement with like all the links and stuff. But you go to pages, you select view all pages, and then you select exam review packets. Okay, cool. So Rachel, for the second part of your question, will I go over the problems? Wait, no, I don't want that. Will I go over the problems on the exam review packet? So here's the thing. I can do problems like the ones on the exam review packet. I won't do those ones explicitly because that is an extra credit assignment. So I won't give answers to the extra credit assignment, but what I will do is do problems similar to those, different numbers, etc. So you can still kind of get that review that you're looking for, and that way you can like see the step-by-step breakdown, similar to what I did with the lab 2 experiments. Like, I'm not gonna do the calculations for you guys so that you can just write in those answers and submit them, but I will do the same type of calculation with different data so that you can compare that to your method to make sure that you're on the right track. Does that make sense? I hope that makes sense. So yeah, so totally. Oh, hang on. I just realized that I published a link, but I don't know. I don't know which lab section you're in, or lecture section. Awesome. If that link doesn't work for you, that link will work if the other one doesn't. Because I'm like, oh yeah, I'll just post a link to the thing, and then I forget that I have 2 different lecture sections in operation right now. Okay. All right, let's see. So we've got a couple questions coming in from the questions about homework in the textbook. Oops. Yes, there totally is. And it's on the packet itself when you open the Google Doc. It's got the due date right up there in the top. Totally. Dude, of course. That is what office hours are for. All right, let's see. All right, so we have a couple questions coming in from chapter 4. Let's see, the first one is number 79. Oops, not part A, part C. Okay. So let's see, 79. Write a balanced complete ionic and net ionic equation for each reaction. All right, so we need to write a balanced, the book calls it a complete ionic equation. In lecture, we called it a total ionic equation, and net ionic equations. All right, and part 79, part C, they give us, and I don't know if this is balanced or not, so we'll find out in a minute. We have aqueous sodium hydroxide plus aqueous acetic acid, which we're going to learn to name soon, producing liquid water and sodium acetate. which is aqueous. All right, so first, we just need to make sure that this equation is balanced to start with, because if we start rolling on the ionic equation stuff and it's not, then we're screwed. Our answer will not be correct. So let's just check things out really quick. We have 1 sodium on our reactant side. We have 1 plus 2 oxygens. We have 1 plus 4, if you're wondering, wait, where's that 4 from? 1, 2, 3, 4. Oh, wait, yeah. So a total of 5, right? 4 coming from acetic acid, 1 coming from sodium hydroxide, and then we have 2 carbons. On our product side, we have 1 sodium, 1 plus 2 oxygen, 2 plus 3 hydrogen, 2 carbon. So it looks like we are totally balanced. That is in the clear. Now for the total ionic equation, we need to take every aqueous ionic compound and break them up, separate the ion pairs. Even though acetic acid is in the aqueous phase right here, it's covalent, so we leave it alone. All right, let's break up every ionic compound. So this is sodium cations. Sodium has a charge of +1, plus hydroxide anions, plus acetic acid, aqueous, producing liquid water. Again, it's a liquid, so we leave it alone. And sodium cations, plus acetate anions, also aqueous. All right, so this is the total ionic equation right here. Now for the net ionic equation, we have to look for spectator ions and cancel them. The only spectator ion, the only thing that's on both sides of the total ionic equation is sodium. So once you cancel sodium, you're left with aqueous hydroxide plus acetic acid producing liquid water and acetates. And this, with all these spectator ions canceled, is the net ionic equation. All right, so that was chapter 4, number 70, part C. The next question is still from chapter 4. It's number 80, part B. All right, let's see. It's the same thing. They want a balanced total ionic and net ionic equations. All right. So let's take a look. 80 part B. All right, here we have aqueous ammonium chloride plus sodium hydroxide, also in the aqueous phase, producing liquid water plus ammonia gas plus sodium chloride, aqueous. As always, you always want to make sure that you're balanced. So let's take an inventory. Nitrogen, hydrogen, chlorine, sodium, and oxygen. We've got 5 elements to account for. Nitrogen is 1. Hydrogen, we've got 4 plus 1, right? 4 from ammonium chloride, 1 from sodium hydroxide, 1 chloride, 1 nitrogen, 1 oxygen. On the product side, we have 1 nitrogen, 2 plus 3 hydrogen, 1 chlorine, 1 sodium, 1 oxygen. So we're all balanced. We're good. Next, we need to write our total ionic equation. So we're looking for all of our aqueous ionic compounds, and we're going to separate those ion pairs. So ammonium chloride, aqueous ammonium chloride separates into aqueous ammonium cations plus aqueous chloride anions. Sodium hydroxide separates into aqueous sodium cations plus hydroxide anions. And this produces liquid water plus ammonia gas plus sodium cations. There's a familiar face. Plus chloride anions. All right, this is our total ionic equation. Now we have to identify our spectator ions to take this to the net ionic equation. And oh, yeah, totally. Okay, awesome. Once I'm done with these, I will totally hit up that question. All right, so to get to our ionic equation, we need to identify our spectator ions, and that's an ion that appears on both the reactants and product side unchanged. One such ion is sodium. Another such ion is chloride. Everything else undergoes some sort of change. So the net ionic equation for this reaction will be aqueous ammonium cations reacting with aqueous hydroxide anions to produce liquid water and ammonia gas. And this is the net ionic equation. All right, so that was 80 part B. And then the last in this topic, or in series of questions that you asked for, was 80 part D. So let's see, 80 part D. All right, this is, here we go. We've got acetic acid. Plus aqueous potassium carbonate. This produces liquid water plus carbon dioxide plus potassium acetate. All right, now again, we just got to do a quick check to make sure we're balanced. Hydrogen, carbon, oxygen, and potassium. So hydrogen, we have 4 plus 2 plus 1, right? Carbon. There's 2 plus 3 oxygen and 2 potassium. All right. Now on our product side, we have 2 hydrogen, 1 plus 2 carbon, 1 plus 2 plus 2 oxygen, and disconcertingly 1 potassium. All right, so this one is not balanced. We have to do some work here. Potassium looks pretty straightforward. We need 2 on our product side to be balanced. This is going to throw everything out of whack because now we have to multiply this by 2 and this by 2. So our carbon count is now 1 plus 4, and our oxygen count is now 1 plus 2 plus 4. But hey, potassium's balanced, right? All right. Oh my gosh, I actually messed up royally already. First, let me just make that clear. We also have 3 hydrogen and acetate, and that gets multiplied by 2. So this is 2 plus 6. All right. So what do we do now? This looks like a hot mess. Well, here's what I'm noticing. Here's what I'm noticing. I'm noticing that carbon, let's zero in on carbon here and here. Carbon is 1 plus 2 on our product side, and it's 1 plus 4. So if we can multiply this thing by 2, it'll balance carbon. So let's go ahead and do that. Let's multiply this by 2, see what happens. Hydrogen gets doubled, that gets doubled, and selectively this oxygen gets multiplied by 2. So this is 2 plus 3. Our carbon count is now 4 plus 1. And our hydrogen count is now 8. And if you check it out, every single element, this one doesn't look balanced, but that's because I did my math wrong. 2 times 2 is not 2, it's 4. Every single element is now balanced. So this is our balanced chemical equation. Now I've got some cleaning up to do. All right. Now that we've balanced our chemical equation, and you always have to check, but once we are, we look at where are our aqueous ionic compounds, because those are the ones that we need to break up to get our total ionic equation. So we'll have 2 molecules of acetic acid that, even though they're aqueous, they don't separate because it's a covalent compound, times, or not, sorry, not times, say chemical equation reacts with 2 potassium cations and 1 carbonate anion to produce wait just a minute. Okay, yeah, no, that checks out. To produce 1 molecule of water, liquid water, plus carbon dioxide, 1 molecule of carbon dioxide gas, plus, now we can break this up, 2 potassium cations and 2 acetate anions. It's negative. All right, so this is our total ionic equation right here. It's pretty long. And now we need to identify our spectator ions to get our net ionic equation. Potassium is on both sides of this reaction unchanged, and it is the only spectator. So our net ionic equation will be 2 molecules of acetic acid in the aqueous phase reacting with 1 molecule of carbonate, producing 1 molecule of water plus 1 molecule of carbon dioxide plus 2 acetate anions. And this is the net ionic equation. All right. So, Kate, thank you for waiting patiently to get to the end of a previous question you asked. Okay, so the second oxidation state example from lecture today. Okay, let me nab that. I have that over here. All right, let's see. Pulling up my lecture notes from chapter 4. All right. So with this one, we have to identify. So we need to find the oxidizing and reducing agents. All right. And we've been given a chemical reaction, lithium. This is called a compound called lithium aluminum hydride, reacting with carbon dioxide to produce this guy, aluminum hydride, and this guy, which shall remain unnamed. Though that's lithium formate. Never mind, it just got named. All right, so we have to find the oxidizing and reducing agents. To do that, we need to know what is oxidized and what is reduced. To determine what is oxidized and what is reduced, we must assign our oxidation states. So this problem will incorporate everything that we talked about in class today. Everything that we talked about in class today. So let's start with lithium aluminum hydride. First off, we know the oxidation state of lithium because it's a main group metal. Well, actually, before we even go there, hydrogen is the only non-metal present, rule number 2. So since it's the only nonmetal, it'll have an oxidation state of -1. Lithium, main group metal, will have an oxidation state of +1. We now have enough to determine the oxidation state for aluminum. All right, so let's take a look. So we've got lithium plus the oxidation state of aluminum plus 4 times the oxidation state of hydrogen is equal to our total charge, which is 0. Lithium, as we know, is +1. Aluminum is yet to be determined. And hydrogen in this compound is -1. All of this is equal to 0. So if we have aluminum +1 minus 4 equals 0, that means aluminum -3 is 0. So aluminum itself has an oxidation state of +3. All right, so that's I wrote that in the wrong layer. All right, there we go, +3. All right, now let's look at carbon dioxide. The final rule states that the most so there's no hydrogen, there's no main group metals. We got to go to the rule number 4. The more electronegative element will take its regular ionic charge. So oxygen is more electronegative than carbon, so it picks up a charge of -2. So carbon plus 2 times the oxidation state of oxygen equals our total charge of 0. So if this is carbon plus 2 times -2 equals 0, means that we've got carbon -4 equals 0. So carbon in this compound has an oxidation state of +4. All right. Moving on to the, oh shoot. Oh, no. I put that in the right layer. Okay. I'm sorry, I'm getting sloppy with my layers this evening. Looking at aluminum hydride. Aluminum has an oxidation, so hydrogen is the only nonmetal in this molecule. So it picks up an oxidation state of -1. Since we have 3 -1s, and they all have to add to our total charge of 0, aluminum must have an oxidation state of +3. All right, and now finally, we're on our last one, and hydrogen's not the only nonmetal. There are other nonmetals present, so it's a +1. Lithium, main group metal, also a +1. Between carbon and oxygen, we've talked about this already in this problem. Oxygen is more electronegative than carbon, so it picks up an oxidation state of -2. And now we can solve for the oxidation state of carbon, because the oxidation state of lithium plus carbon plus our 2 oxygens plus our hydrogen must equal our total charge, which is 0. Lithium's +1. +1, there we go. We do not yet know carbon's oxidation state. We do know oxygen is -2. Hydrogen is +1. This is all equal to 0. So 1 plus 1 is +2. 2 times -2 is -4. So carbon -4 plus 2 equals 0. that means carbon minus 2 is 0. So in this compound, carbon has an oxidation state of plus 2. All right, we have at this moment successfully assigned all of our oxidation states. Now we have to find the ones that are changing. All right, we've got a lot going on, but we're looking for anyone whose oxidation state changes. All right. Now, because we need to find the elements that are oxidized and reduced so we can identify the oxidizing and reducing agent. First, the first one that jumps out at me is carbon. Carbon goes from a positive 4 to a positive 2. All right. That tells me if you go from positive 4 to positive 2, you've picked up negative charge along the way. That means you have gained electrons. And Leo says, gain electrons reduction. Carbon is reduced. All right. But now what's oxidized? One thing you'll notice is lithium starts at positive 1, ends at positive 1. No change. Aluminum starts at positive 3, ends at positive 3. No change. Now, what makes this one challenging is you're like, well, hydrogen starts at negative 1, but in one compound, it ends at negative 1. In another compound, it ends at positive 1. Which one do you go with? Here's the thing. If you notice any change, it doesn't matter if there's another atom on the product side that has an unchanged oxidation state, it doesn't alter the fact that hydrogen, one of these hydrogens, starts at a negative 1 and ends at a positive 1. That is a change in oxidation state. That is enough for us to go on. So if you start at negative 1 and end at positive 1, you've lost negative particles, which means you've lost electrons. And Leo, says Gerd, Leo is lose electrons, oxidation. Hydrogen is the atom that is oxidized. All right. So we figured out what element is reduced, what element is oxidized. But when you look at carbon, carbon is here. What compound, what molecule reacts with carbon causing the oxidation? And the answer to that is lithium aluminum hydride. Lithium aluminum hydride, LiAlH4, reacts with carbon, causing the reduction. So lithium aluminum hydride is the reducing agent. All right. We know that hydrogen is the element that is oxidized. What compound reacts with hydrogen, causing that oxidation? In this reaction, it's CO2. In this reaction, carbon dioxide is the oxidizing agent. All right, so CO2 is the oxidizing agent. Lithium aluminum hydride is the reducing agent. So, okay, that is how you tackle any problem where they're asking you to identify the oxidizing agent and reducing agent. It's impossible to do by itself. You have to have a chemical equation to evaluate. All right, so that's the first part of your question. The second part of your question, you're wondering about antioxidants and oxidants in the body, and how oxidation state relates to this topic. So antioxidants are one of those categories of things that people are like, oh, those are so good, without really knowing. Well, I shouldn't say without knowing why. Some people do. Not everybody does. I know for the longest time I just heard them and thought antioxidants good, and they are good for us. But I didn't understand the chemistry behind it. So a lot of damage that's done to your body, ironically enough, comes from the air that we breathe. So we're breathing O2, and this is actually something that we'll be discussing towards the end of this semester. You'll see why this is the case. Oxygen, O2, is something called a free radical, which means that it has at least one unpaired electron. Oxygen is a di radical. It has two unpaired electrons, and free radicals tend to be very reactive. They react with lots of different things, and they can wreak damage in our DNA, our molecular structure. They can like tear it apart, mess things up, and so antioxidants are compounds that have electrons that they can give to satisfy, the free radicals like O2 that get into our bodies and start wreaking havoc. Like we need oxygen, which is why I'm breathing right now, and my blood cells are carrying it where it needs to go. But excuse me, I apologize for the yawn. It's the mileage, not the company. So when it gets into our system, but not through our respiratory system, it can deal a lot of damage. And antioxidants are kind of like armor against oxidants, rather than the oxidant reacting with our DNA or the molecular structure of our cells. The antioxidant is like, here, I've got electrons, be satisfied. And the oxidant's like, thank you, and it eats it up. And they do a little mini redox reaction instead of the oxidant tearing our body apart, looking for a redox reaction to stabilize it. So that's kind of how oxidants and antioxidants, kind of the basic thing of what they do in the body. Oxidants are looking to consume electrons. Antioxidants give away electrons. So the oxidants, ironically enough, are reduced, and the antioxidants are oxidized, rather than our body getting oxidized, which is not good for us. So yeah, that is an excellent conceptual question. Ah, Rin, that is an excellent question. Okay, so whenever you have any metal, so any metal in a chemical equation when it's by itself, will have its charge superscripted to the left of the symbol. So, for example, if you saw this, superscripted to the left of the symbol, charge equals +1. If you saw this, here's vanadium 5, superscripted to the left of the symbol, the charge is +5. If you had this in a chemical equation, that would be aqueous up there. Let's say this is a solid. As always, the charge is superscripted to the left of the symbol, and you may be going, but Josh, there's nothing there. To which I would say, exactly, the charge here is 0. So if you see a metal alone in a chemical equation, the charge is always superscripted to the left. If you don't see any charge written up there, that means that its charge is 0. Okay, let's see. So when it talks about not filling the volumetric flask, okay, here. 1 second. Let me oops. Okay, so here, let me see. So when it talks about not filling the volumetric flask all the way to the mark, I said that the percents would stay the same. Okay, so here's the thing. So let's visualize this for a second here. So we have a volumetric flask, right? That is calibrated to measure exactly 100.00 milliliters of volume. And we're going to use this in our calculations, all right? That is the volume that we use in our calculations. If, however, you don't fill all the way up to the line, all right, if you almost fill all the way up, but not quite all the way there, what that means is that your actual volume is less than 100 mils. But you don't know how much less. So you would still end up using 100 milliliters in your calculation, even though the actual volume was less. So this would decrease the accuracy of your calculation. Because your assumption that you've used 100 milliliters of solution is incorrect. You've actually used less. It would decrease the accuracy of your calculation by making your percents calcium and your percent chloride higher than it should be, or than they should be. Because you'd be multiplying in the calculation by 100, when in reality, if you're using an accurate volume, you'd be multiplying by less than 100 milliliters because you used less. Hopefully that makes sense. You are so totally welcome. All right, let me see. Follow-up question. Murat, that is an excellent question. All right, here's the mathematical origin. So percent mass of calcium, as you said, grams of calcium over grams of calcium chloride times 100%. Well, times 100. That makes it a percentage. All right, now let's think for a minute about where you get that numerator. All right, where we get our mass of calcium. And you get your mass of calcium basically you have your ISE reading, which gives you a reading in milligrams per liter, and then you multiply by the volume of your flask in liters. Now, hang with me here. If the actual volume was less than 100.00 milliliters, but you use 100.00 milliliters in this calculation, your calculated mass of calcium will be higher than it should be. And if your numerator, if this right here, this is too large or larger than it should be, then your percentage will also be larger than it should be. Does that make sense? Okay, let's see. Ah. Right, your logic is spot on. Oh, let's see. Anthony, just seeing your question. For post-lab, question 2C, it asks if you didn't quantitatively transfer all the solid calcium carbonate to the volumetric flask, would the percent mass of calcium go up or down? Well, so let's think about it. So if you don't transfer all the calcium chloride, your ISE readings will be lower than they should be. This will result in deflated values for percent calcium and percent chloride. Kyle, let me see. Would you like the worksheet and scratch work calculations to be all one PDF, or can they be two PDFs? Great question. All one PDF, please. Alrighty, and that is gonna that's gonna do it for me tonight. It was actually a really awesome office hour. We were talking for a majority of it. Thank you everybody who came out, who brought your awesome questions to get answers, but also benefit the rest of the class. It takes bravery to ask questions, and so I applaud you. I will catch you all on Wednesday afternoon for our next lecture, and then I'll be here again on Wednesday night for another office hour sesh. Take it easy, dudes.